Welcome to the Deep Sleep Science channel. Tonight, we're stepping gently into a world where particles can be in two places at once, where empty space quietly flickers with energy, and where light behaves both like a wave and like tiny packets traveling across the universe. It's a place so strange that it powers stars, builds atoms, and even helps guide your phone across the Earth. As you listen, you'll discover how the smallest pieces of reality shape everything around you, from the glow of distant galaxies to the technology you use every day. And if you'd like to return to this calm journey again, you might consider leaving a like, subscribing, or sharing a quiet comment before you drift off. Quantum physics tells us that nature is not always smooth and continuous at its deepest levels. Many physical quantities come in tiny set amounts, or quanta, as if the universe sometimes prefers small packets instead of an unbroken flow. That idea changed science completely, because it suggested that the microscopic world follows rules very different from the ones we notice in ordinary daily life. One of the most surprising discoveries in quantum theory is that light can behave like a stream of particles called photons. Even though we often think of light as a wave spreading through space, experiments showed that it can also arrive in separate little bundles of energy. This strange dual character is one of the first hints that the quantum world does not fit neatly into classical categories. Matter also carries this wave-like quality. Electrons, atoms, and even larger objects can, under the right conditions, produce interference patterns that look very much like waves overlapping and combining. So in quantum physics, being made of matter does not prevent something from also acting in a wave-like way. A quantum system can exist in a superposition, which means it can occupy a blend of possible states at the same time, until a measurement or interaction picks out a definite result. This is not just a poetic way of speaking. It is a real feature of the theory, and it has been tested again and again in experiments. Superposition is one of the reasons quantum physics feels so unfamiliar and so powerful. Quantum interference happens because the different parts of a superposition can combine with one another. Sometimes they strengthen each other, and sometimes they cancel each other out, much like ripples on water meeting in a pond. This interference is not a small detail. It sits at the heart of many quantum effects, from famous double-slit experiments to advanced quantum technologies. Quantum tunneling is one of the most astonishing behaviors in all of physics. It allows a particle to pass through a barrier that, according to classical physics, it should not have enough energy to cross. In the quantum world, the particle is described by a spread-out wave-like state, and that gives it a real chance of appearing on the other side of the barrier. This same tunneling process helps power the sun. Deep inside a star, positively charged protons repel each other strongly, and by classical reasoning they should have great difficulty getting close enough to fuse. But quantum tunneling gives them a way through that repulsion barrier. Without this effect, stars like our sun would shine very differently, or perhaps not in the same steady way at all. Entanglement is another deep quantum feature, and it reveals that two systems can become linked in a way that prevents them from being fully described independently. Their properties become connected as parts of one larger quantum state. Even when the systems are separated by a great distance, measurements on them can show correlations that classical ideas struggle to explain. Those entangled correlations do not allow faster-than-light communication, because each individual result still appears random on its own. But when the results are later compared, the relationship between them reveals something genuinely quantum. This makes entanglement both mysterious and useful, since it lies behind many modern ideas in quantum communication and computing. Bell inequalities were invented to test whether hidden classical explanations could reproduce all the predictions of quantum mechanics. When experiments violated those inequalities, They showed that the world does not behave according to a simple picture of local hidden variables. These tests did not make quantum theory less strange. They made its strangeness harder to escape. Experiments honored by the 2022 Nobel Prize in Physics confirmed these violations of Bell inequalities with remarkable care. They strengthened the case that the quantum description is not just a mathematical trick, but a real guide to how nature behaves. In that sense, quantum mechanics has not only survived philosophical debate, it has been reinforced by direct experimental evidence. Antimatter is another awe-filled part of quantum physics. Relativistic quantum theory predicts that ordinary particles should have partners with opposite charge, and those partners are real. The electron, for example, has an antimatter counterpart called the positron. This shows that the equations of quantum physics can reveal entire categories of matter before scientists fully explore them in the laboratory. When matter and antimatter meet, they can annihilate and turn their mass into radiation or other particles. This is one of the clearest examples of the deep relation between mass and energy. It also reminds us that particles are not little eternal pebbles. Under the right conditions, they can transform completely into other forms of physical reality. CERN has gone far beyond simply producing antimatter. Its experiments have trapped antihydrogen atoms long enough to study them in detail, which is remarkable because antimatter usually disappears the moment it touches ordinary matter. Holding these atoms in place allows scientists to examine whether antimatter obeys the same internal quantum rules as the familiar matter around us. Researchers have even laser-cooled antihydrogen, bringing a standard tool of atomic physics into the study of antimatter. Cooling helps reduce motion, which makes delicate measurements far more precise. The fact that such careful techniques can now be applied to antimatter shows how far quantum control has advanced. Quantum fluctuations belong to another breathtaking idea. Even what we call empty space is not truly empty. In quantum field theory, vacuum is the lowest energy state of fields, not a featureless void. That means small, unavoidable fluctuations remain, and these subtle, restless variations are part of the fabric of the universe itself. Those fluctuations are not just abstract theory. They are important enough that engineers working on LIGO, the observatory that measures incredibly tiny ripples in space-time, must account for them. When an instrument becomes sensitive enough, even the quantum character of emptiness can matter. That is a beautiful reminder that quantum physics reaches into places that once seemed far beyond its scale. Bose-Einstein condensation is one of the most dramatic examples of quantum behavior appearing on a larger scale. When many bosons are cooled enough, they can gather into the same lowest quantum state and begin to act in a deeply collective way. Instead of behaving like many separate particles, the system starts to resemble one shared quantum object. The first gaseous Bose-Einstein condensates were created in dilute alkali atoms and marked a historic achievement in physics. They showed that under the right conditions, quantum rules can organize a large collection of particles into a single coherent state. It was a striking confirmation that quantum physics is not limited to microscopic curiosities. Superconductivity is another grand quantum state, one in which electrical resistance disappears below a critical temperature. In that state, electric current can flow without the ordinary losses that happen in normal materials. This is not simply a better conductor. It is a distinct quantum phase of matter with its own collective order. The BCS theory explained conventional superconductivity by showing that electrons can form bound pairs called Cooper pairs. Even though electrons are fermions and normally resist crowding into similar states, pairing changes their collective behavior. Through that pairing, they can join a coherent quantum state that supports resistance-free flow. Modern particle physics is built on quantum field theory, where fields are treated as the fundamental ingredients of nature and particles appear as excitations of those fields. In this picture, a particle is not just a tiny object flying through emptiness. It is more like a localized ripple or disturbance in an underlying field that fills space. The Standard Model grows out of this quantum field picture. It organizes the known elementary particles into matter particles and force-carrying particles, giving a unified framework for much of known microscopic physics. It is one of the most successful scientific theories ever created, even though scientists know it is not the final word on everything. In the Standard Model, quarks and leptons make up matter. These are the basic building blocks that, in different combinations, produce the familiar material world. Electrons belong to the lepton family, while protons and neutrons are built from quarks bound together. This structure helps show how the everyday world arises from a small set of fundamental ingredients. The Higgs field adds another sweeping idea to the quantum picture. It is a field that fills space, and particles interacting with it acquire mass through that interaction. The Higgs boson is the detectable quantum excitation of this field, and its discovery confirmed that this strange but elegant part of the theory is physically real. The Standard Model is incredibly successful, yet it still does not explain everything. It does not fully account for dark matter, and the origin of neutrino masses goes beyond its simplest form. So quantum physics is both a triumph and an open frontier. It explains a vast amount while still leaving room for deeper discovery. Quantum physics describes the world using quantum states, which are mathematical descriptions containing the probabilities of future measurement outcomes. A quantum state is not merely a label attached to a particle. It is a compact way of expressing what can be known and predicted about a system before a measurement is made. Measurement in quantum physics is probabilistic. That means the theory usually does not promise one guaranteed outcome for a single event. Instead, it tells us the chances of the different outcomes we may observe. When the same experiment is repeated many times, those probabilities reveal themselves in stable statistical patterns. The uncertainty principle expresses one of the built-in limits of the quantum world. It does not just mean our tools are clumsy or incomplete. It means certain pairs of quantities are linked so deeply that making one more definite naturally makes the other less definite. This is a structural feature of reality as described by the theory. Position and momentum are the best-known uncertain pair. The more sharply a particle's position is defined, the less sharply its momentum can be known, and the reverse is also true. This is not because the particle is hiding information from us. It is because the quantum state itself does not allow both quantities to be perfectly fixed at the same time. Quantum mechanics explains why atoms are stable. In a purely classical picture, electrons moving around a nucleus should lose energy and spiral inward. But the quantum description replaces that unstable picture with allowed states and quantized structure. Because of that, atoms do not collapse. They persist as stable building blocks of matter. The theory also replaced the older image of electrons traveling in neat little planetary paths around the nucleus. Instead, electrons in atoms are described by orbitals, which are probability distributions showing where they are likely to be found. This gives atomic structure a softer, more cloud-like description rather than a rigid mechanical one. The periodic table depends on this quantum structure. The way electrons fill shells and orbitals determines how atoms bond, react, and organize into chemical families. So chemistry, at its deepest level, rests on quantum rules. The familiar patterns of the elements are shaped by invisible microscopic structure. The Pauli exclusion principle is one of the key reasons matter has structure. It says no two electrons in the same atom can share the exact same full set of quantum numbers. Because of that rule, Electrons stack into layered shells rather than all collapsing into the lowest possible state. This exclusion principle is why atoms build up rich internal structure and why ordinary matter takes up space in the way it does. Without it, the architecture of atoms and solids would be profoundly different. A quiet mathematical rule at the quantum level helps create the stable diversity of the visible world. Electron spin is another essential part of the quantum picture. It behaves mathematically like angular momentum, but it should not be imagined as a tiny ball literally spinning around. It is a built-in quantum property, and for electrons it leads to two possible measurement outcomes along a chosen direction. Because spin comes in quantized values, it gives matter a kind of discrete internal character. This affects magnetism, atomic structure, and many modern technologies. Quantum physics often takes qualities that might seem smooth in classical thinking and reveals them to be sharply quantized underneath. An atom absorbs or emits light only when the photon energy matches the gap between two allowed energy levels. That is why atomic spectra appear as sharp lines rather than continuous smears. Each line corresponds to a specific quantum transition, making atoms behave like tiny natural resonators with fixed notes. Quantum jumps between atomic energy levels are real transitions, not gradual sliding motions. When an atom changes state, it moves between allowed levels rather than drifting continuously through forbidden ones. This idea was once shocking, but it became one of the foundations of modern atomic physics. Bound quantum states have discrete energies, and that is why atoms emit distinct spectral lines. Free particles, by contrast, can still be described quantum mechanically without being restricted to the same kind of discrete energy ladder. This difference between bound and free behavior helps define much of atomic and molecular physics. The Schrödinger equation tells us how a quantum state changes over time when the system is isolated from outside disturbance. It plays a role somewhat like Newton's laws in classical mechanics, but it governs wave-like probability amplitudes rather than definite trajectories. Through it, quantum evolution can be calculated with great precision. That evolution is smooth and reversible as long as the system remains coherent. In other words, before measurement or environmental disturbance scrambles the state, its motion follows a precise mathematical development. This calm internal order is one of the quieter beauties of quantum theory. Many quantum effects become difficult to observe in ordinary life because the environment quickly disrupts the delicate phase relationships in a system. This process is called decoherence. It helps explain why the world of tables, trees, and falling cups looks classical, even though everything is built from quantum ingredients. Decoherence does not mean quantum physics stops being true at large scales. Instead, it means large systems are usually so entangled with their surroundings that their clean quantum features are hidden from us. The classical world may be thought of, in part, as the quantum world viewed through constant environmental disturbance. Quantum theory does not remove causality altogether. What it changes is the kind of certainty we can have about outcomes. Rather than giving guaranteed results for every individual event, it gives lawful probabilities that become clear through repeated measurements. The order is statistical, but it is still real and remarkably reliable. Quantum mechanics has passed an extraordinary number of experimental tests and remains one of the most accurate scientific frameworks ever developed. Again and again, it has predicted subtle behaviors that later appeared in the laboratory. However strange its language may seem, its practical success is undeniable. Modern particle physics says that photons are excitations of the electromagnetic field. So a photon is not just a tiny marble of light. It is a quantum ripple in a field that extends throughout space. This view is part of the broader shift from thinking mainly in terms of objects to thinking in terms of fields and their excitations. Electrons, too, are described in quantum field theory as excitations of an electron field. In this way, both matter and force are woven into a common field-based language. The universe, in this picture, is filled with underlying fields, and what we call particles are the localized ways those fields can vibrate. Bosons and fermions form two great families of quantum particles. Bosons can share the same state in large numbers, while fermions obey the exclusion principle and resist piling into one state. This simple distinction has enormous consequences, shaping everything from lasers to atomic shells to the possibility of Bose-Einstein condensation. Quantum electrodynamics is the quantum field theory of light and electric charge. It describes how photons and charged particles interact, and it has achieved some of the most precise agreements between theory and experiment ever recorded in science. Its success shows how exact quantum theory can become when carefully developed and tested. Atomic clocks reveal how quantum physics reaches into practical life. They use quantum transitions inside atoms or ions as extremely stable reference frequencies. Because those transitions are so consistent, atomic clocks can measure time with astonishing precision, supporting technologies that modern society quietly depends on. Optical clocks push this precision even further by using light frequency transitions that are much higher than microwave frequencies. Higher frequencies allow finer timing resolution, which is why optical clocks have become such an important frontier in metrology. They show that quantum transitions can serve not just as curiosities, but as the basis for the finest measurements humans can make. GPS and similar navigation systems rely on atomic clock technology, which means quantum timing already supports everyday travel, mapping, and communication. Even when people use navigation casually, they are depending on exquisitely precise quantum-controlled timekeeping. It is a gentle reminder that quantum physics is not far away. It is woven quietly into modern life. Quantum physics is therefore not only a theory of the microscopic world. It is also a foundation for measurement science, engineering, and many of the most precise tools humanity has ever built. From atoms and light to clocks, sensors, and fields, it offers one connected framework for an enormous range of physical reality. The Standard Model arranges the known elementary particles into a clear quantum family tree. In the broadest sense, it separates them into matter particles, which make up the substance of the world, and force-carrying particles, which allow those pieces of matter to interact. This organization matters because it shows that the universe is not built from an endless zoo of unrelated pieces. Instead, a surprisingly small set of quantum ingredients can account for an enormous amount of physical structure. Within that framework, quarks and leptons are the basic matter particles. Leptons include familiar particles like the electron, while quarks combine to form larger particles, such as protons and neutrons. This division is helpful because it tells us that ordinary matter has layers. The things we can hold and see are made of atoms. Atoms contain nuclei and electrons, and the nuclei themselves are built from still smaller quantum components. The photon carries the electromagnetic force in quantum theory. That means light is not just illumination for our eyes. It is also the messenger that allows electrically charged particles to influence one another. Whenever atoms emit light, whenever electrons repel or attract, and whenever electromagnetic radiation travels through space, the photon is part of the underlying quantum story. Gluons carry the strong force, which binds quarks together inside protons, neutrons, and other hadrons. Their role is essential, because quarks do not simply sit side by side on their own. They are held together by an intense interaction that becomes especially important at very small scales. Without gluons, the atomic nuclei that make up ordinary matter would not have the structure we know. The W and Z bosons carry the weak force, which is involved in processes like radioactive beta decay. This force is not as familiar in daily life as electromagnetism, but it is deeply important in nuclear processes and in the behavior of elementary particles. It helps explain why some particles transform into others, showing that the quantum world is not static, but full of carefully governed change. The Higgs boson is the quantum ripple of the Higgs field. Thinking of it this way can make the idea more intuitive. Just as a ripple on water reveals that water is there, the Higgs boson reveals the presence of the Higgs field. Detecting the particle confirmed that this invisible field is not only a mathematical convenience, but a real ingredient of the universe. Not all of the mass of ordinary matter comes from the Higgs field in exactly the same way. A large part of the mass of protons and neutrons comes from the energy of quarks and gluons interacting inside them. This is a beautiful example of how mass in modern physics is not always just a simple built-in property. Sometimes it emerges from motion, binding, and the energy stored inside a quantum system. Quarks are never normally observed alone because the strong interaction confines them inside composite particles. This means nature does not let them drift freely in everyday conditions the way electrons can. Instead, quarks remain bound into larger objects, which is why we encounter protons and neutrons rather than isolated quarks in ordinary matter. Protons and neutrons are not fundamental particles in the deepest sense. Each one is made from quarks bound together by gluons. This matters because objects once thought to be indivisible turned out to have their own internal structure. Quantum physics repeatedly reveals that what looks simple on one level often contains a deeper level beneath it. Mesons are another family of quark-based particles made from a quark and an antiquark. They are different from protons and neutrons, yet they are built from the same basic ingredients arranged in another way. This shows that the quantum world allows multiple stable or short-lived structures to emerge from the same small set of building blocks. Neutrinos are extraordinarily elusive quantum particles. They interact so weakly with matter that huge numbers of them can pass through an entire planet with hardly any interaction at all. Because of this, scientists need enormous detectors and very careful methods to study them. Their ghostly behavior makes them one of the most subtle inhabitants of the quantum world. Neutrino oscillations show that one kind of neutrino can change into another as it travels. A neutrino created in one identity does not always remain in that identity forever. This transformation happens because the quantum description of neutrinos involves a deeper structure than simple fixed labels. Their behavior unfolds over distance and time in a way that only quantum theory makes clear. The discovery of neutrino oscillations was especially important because it implied that neutrinos have mass. That meant the simplest version of the Standard Model was incomplete. In this way, neutrinos quietly opened a door to physics beyond one of science's most successful theories. Sometimes the smallest and hardest to detect particles end up revealing the biggest gaps in our understanding. Particle accelerators are not only machines for violent collisions, they are also tools for exploring the rules that govern quantum fields and particles. By giving particles carefully controlled images and then studying what appears after collisions or interactions, scientists can test the structure of matter with extraordinary depth. These machines are like microscopes for the deepest levels of physical law. Detectors in particle physics do not watch particles the way eyes watch moving objects. Instead, they record traces of quantum interactions, such as deposited energy, light flashes, or ionized material. From those traces, researchers reconstruct what likely happened. So the process of seeing in modern physics is often indirect, relying on careful interpretation of physical signatures. The Standard Model remains stunningly successful, yet it does not explain everything known or suspected in the universe. It does not fully account for dark matter, and it does not give the full story behind neutrino masses. This makes it both a triumph and a signpost. It shows how far quantum physics has come, while also pointing toward what remains unfinished. Cesium clocks define the C-second using a specific quantum transition in the cesium atom. This means the basic unit of time is no longer tied to Earth's rotation or any everyday cycle. It is anchored to a repeatable process inside matter itself. That gives timekeeping a deep quantum foundation and makes it far more stable and universal. Modern optical clocks push precision even further, with uncertainties approaching astonishingly tiny fractions, near parts in 10 to the 18th. At that level, the clock is so precise that even very slight effects from motion, gravity, or environment can matter. These clocks show how quantum transitions can become not just accurate references, but some of the finest measurement tools ever created. Some of the most accurate optical clocks use trapped ions rather than large clouds of atoms. A single ion can be isolated, controlled, and measured with exquisite care. There is something elegant about that. One tiny charged particle, held in place and protected from disturbance, can become the heart of a clock whose precision rivals anything humans have built. Other optical clocks rely on neutral atoms arranged in optical lattices, where laser light forms a kind of repeating trap. In these systems, many atoms can be held in orderly positions and measured together. This combines the stability of quantum transitions with the power of working with an ensemble, giving another route toward ultra-precise timekeeping. Laser cooling slows atoms by using the momentum of photons. Although light feels weightless to us, its momentum is enough to gently push on atoms and reduce their motion when arranged in the right way. This is one of those quantum ideas that feels almost magical at first. Light, which usually seems like something that illuminates, becomes a tool for slowing matter down. Laser cooling and trapping open the way to studying atoms at incredibly low temperatures, where delicate quantum effects become easier to preserve and examine. At high temperatures, motion tends to blur out fine behavior. At very low temperatures, quantum structure can stand out more clearly. Cooling, therefore, becomes not only a technical trick, but a way of revealing a quieter layer of reality. Ion traps can isolate a single ion for extremely precise measurements. That isolation is important because the less a particle is disturbed by its surroundings, the more clearly its quantum behavior can be measured. In this way, a trap becomes a kind of peaceful environment, allowing one tiny system to speak very clearly about the laws of nature. Trapped ion methods have been used both to test quantum electrodynamics and to build exceptionally precise clocks. This combination is striking. The same platform can serve deep fundamental science and practical measurement technology. That is one of the recurring strengths of quantum research. The boundary between pure understanding and useful application is often very thin. Quantum logic spectroscopy allows one ion to help reveal the state of another ion that is harder to measure directly. In simple terms, one controllable ion can act almost like an interpreter for a more stubborn partner. This method extends precision measurement to systems that would otherwise be difficult to access and shows how clever quantum control can expand the reach of spectroscopy. Some ions in precision clocks are not cooled directly with lasers. Instead, they are cooled sympathetically by another trapped ion through shared motion. This is a lovely example of indirect control. One particle does not need to be manipulated on its own if it can be gently guided through a carefully coupled neighbor. Atom interferometers use superpositions of different atomic paths to measure motion, gravity, and time with great sensitivity. The atom is placed into a situation where it effectively explores more than one path at once. And when those paths are later recombined, the interference carries precise information. This turns the wave nature of matter into a measurement tool. In atom interferometry, a laser pulse can act like a beam splitter for matter waves. Instead of dividing a beam of light, it divides the quantum path of an atom. This is conceptually beautiful because it shows that techniques once associated mainly with optics can be translated into the behavior of matter itself. A later laser pulse can redirect the atomic paths, acting like a mirror for matter waves. By shaping and guiding the motion of the quantum state in this way, researchers can build full interferometer sequences. These sequences let atoms travel, separate, and reunite in a controlled manner, making subtle influences measurable through the final interference pattern. The longer the atoms remain coherent before they are brought back together, the more sensitive the interferometer can become. Time matters because the different paths need enough opportunity to accumulate measurable differences. This is why coherence is so valuable. It preserves the quiet quantum relationship between paths long enough for nature to write useful information into it. Space is especially attractive for atom interferometry because free-falling atoms can remain nearly motionless relative to the instrument for longer periods. That extended calm can improve sensitivity by allowing longer measurement times. In this way, orbit and microgravity are not only environments for astronauts. They can also become gentle laboratories for the most delicate quantum measurements. Quantum projection noise appears because, when atoms are measured, they are forced into definite outcomes. Even if the preparation is excellent, there is an unavoidable statistical grain to the result. This is not sloppy engineering. It is part of the quantum structure of measurement itself, and it becomes important when experiments aim for very high precision. Shot noise in atomic and optical measurements is another important quantum limit. When signals are made of separate quanta, whether photons or atoms, the counting statistics introduce fluctuations. As measurements become more refined, these fluctuations stop being small background details and become central design challenges. Ramsey's method of separated oscillatory fields became a powerful way to make very sharp resonance measurements in atoms and molecules. By letting a quantum system evolve between two carefully timed interactions, the method creates interference that sharpens the measured signal. It is a beautiful demonstration of using time, coherence, and phase to increase precision. The hydrogen maser is a quantum device that uses stimulated emission in hydrogen to generate a highly stable microwave signal. In that sense, it is a close relative of the laser, but in the microwave domain. Devices like this show how quantum transitions can be harnessed not only for light production, but also for remarkably steady frequency references. The development of laser cooling directly helped make possible the later study of ultracold dilute gases and the creation of Bose-Einstein condensates. In science, progress often comes in linked steps. A technique developed for one purpose opens the door to a much larger discovery later on. Laser cooling was one of those gateway achievements. Quantum spectroscopy can reveal tiny shifts in energy levels caused by magnetic fields, electric fields, motion, or even relativistic effects. In other words, the spectrum of a system can act like a very sensitive diary of everything influencing it. Small changes in the environment or in fundamental physics can leave measurable fingerprints in these transitions. Optical frequency combs made it practical to connect optical frequencies to ordinary clock measurements. Before that, the enormous gap between optical oscillations and countable electronic signals was a serious challenge. A frequency comb acts like a bridge, allowing the fast rhythm of light to be linked cleanly to the slower world of human measurement systems. Atomic clocks are useful for much more than telling time. Because they are so sensitive, they can test aspects of fundamental physics and even detect tiny differences in gravitational potential. That means a clock can also behave like a sensor. When time is measured precisely enough, it begins to reveal features of space, motion, and gravity. Networks of atomic clocks in space have been proposed for navigation, communication, and geodesy. If clocks can be distributed and compared across large distances with enough stability, they become part of a larger sensing system. In that way, quantum timekeeping can help map not just time itself, but position and the structure of gravitational environments. Very long baseline interferometry in astronomy depends on ultra-stable atomic clock references at widely separated antennas. When telescopes on Earth work together across great distances, their signals must be aligned with extraordinary precision. Quantum-controlled timing makes that possible, allowing distant instruments to behave like one enormous virtual telescope. Quantum sensors in space are being explored because the space environment can improve some kinds of measurement. Longer freefall, reduced disturbances in certain situations, and access to different gravitational conditions can all help. This shows that the future of quantum physics is not confined to laboratories on Earth. It may extend naturally into orbit and beyond. Some spaceborne clocks already outperform older GPS-style clocks in stability. This is a reminder that quantum technology is not standing still. The clocks that quietly support navigation and timing continue to improve, and each improvement opens the door to new scientific and practical possibilities. Quantum measurements are so precise that tiny imperfections in the environment can become major problems. Slight temperature changes, stray electric fields, tiny vibrations, or minute magnetic disturbances can all matter. The better a measurement becomes, the more the surrounding world has to be tamed. Precision at the quantum level often means mastering details that would once have seemed trivial. In atomic physics, coherence time often determines how useful a quantum state will be for sensing or computation. A state may be elegant in theory, but if it loses coherence too quickly, its usefulness is limited. Long coherence is like having more quiet time in which the system can evolve in a controlled and meaningful way before the environment interrupts. The narrower an atomic transition line is, the better it can serve as a frequency reference. A narrow line means the transition energy is very well defined, which in turn allows more precise timing and measurement. This is one reason researchers care so much about isolating systems and reducing noise. Cleaner transitions lead to better standards. High-resolution spectroscopy depends on protecting atoms or ions from disturbances that would broaden or shift their frequencies. That means careful control of fields, motion, temperature, and environment. In these experiments, precision is not achieved by one dramatic trick, but by many quiet acts of control, layered together. Quantum control in atomic systems has advanced to the point where researchers can prepare, manipulate, and read out single particle states with impressive reliability. This represents a major shift from the early days of quantum theory. What began as a framework for explaining strange behavior has become a toolkit for steering that behavior with care. Single particle experiments are especially valuable because they remove the confusion that can come from large, uncontrolled groups. When one ion or one atom is isolated, its quantum behavior can be examined much more directly. This gives physicists a cleaner window into the theory and a better platform for precise tests. Atomic recoil from absorbing or emitting a photon is very small, but it is real and measurable. This recoil matters in precision experiments because even tiny momentum kicks can influence the state of an atom over time. Once again, quantum physics teaches that effects which seem negligible at everyday scales can become crucial when measurements are refined enough. Ultra-cold atoms can be arranged in regular patterns using light, creating artificial crystal-like systems for quantum simulation. These engineered arrays allow scientists to build simplified models of complicated materials or interactions. Instead of calculating everything directly, researchers can let one quantum system imitate another. Quantum simulations with atoms are useful because some quantum systems are too complex to calculate exactly on ordinary computers. By constructing a physical system that follows similar rules, researchers can study behavior that would otherwise remain out of reach. This makes quantum simulation a powerful bridge between theory and experiment. Quantum behavior in dilute gases becomes especially vivid near absolute zero, where thermal motion no longer overwhelms subtle phase relationships. At those extremely low temperatures, the hidden order of the quantum world becomes much easier to observe. Cooling, in that sense, does not merely slow matter down. It allows deeper patterns to emerge. The path from laser cooling to ultra-cold matter shows how improved control of a single quanta can reveal entirely new states of matter. What begins with handling one photon and one atom carefully enough can eventually lead to collective quantum systems with remarkable properties. This is one of the gentlest but deepest lessons of modern physics. When control becomes fine enough, whole new worlds of behavior come quietly into view. The photoelectric effect showed that light can remove electrons from matter one packet at a time, rather than by slowly warming them loose the way a classical wave picture might suggest. This was a major turning point because it revealed that light sometimes delivers energy in separate, indivisible amounts. In simple terms, it is as if light arrives not only as a spreading wave, but also as tiny payments of energy, and only payments large enough to cross a threshold can free an electron. Wave-particle duality does not mean that a quantum object changes its mind and becomes either a wave or a particle in the ordinary everyday sense. It means our classical categories are too limited. A quantum object can produce wave-like interference in one kind of experiment and still arrive in localized detection events in another. The deeper lesson is that the quantum world cannot be fully described by copying familiar pictures from daily life. A quantum wave function is not a physical wave in the same sense as a sound wave in air or a ripple in water. It is a mathematical description that helps us calculate the probabilities of different outcomes. That may sound abstract, but it is extremely powerful. The wave function tells us how likely a particle is to be found in different places or states, and how those probabilities evolve over time. Normalizing a wave function simply means making sure the total probability adds up to 1. Since a particle must be found somewhere if we perform the right measurement, the full spread of possibilities has to sum to certainty. This is one of those quiet but important rules in quantum theory. It keeps the mathematics tied to physical reality and ensures the probabilities remain meaningful. Quantum mechanics uses operators to represent measurable quantities such as position, momentum, and energy. Rather than treating these quantities as simple numbers from the beginning, the theory uses mathematical actions that operate on quantum states. This formal structure may seem unusual at first, but it gives the theory its great flexibility and precision. It is one reason quantum mechanics can handle such a wide range of physical situations. When two quantum operators do not commute, the order in which you apply them matters, and that mathematical fact is closely connected to physical uncertainty. In ordinary arithmetic, many operations can be swapped without changing the result. In quantum mechanics, that is not always true. This difference is not a technical curiosity. It reflects something deep about how certain physical properties are related in the quantum world. A quantum system can be prepared in an eigenstate of one observable, which means that measurement of that particular property will give a definite result. In that special state, the uncertainty for that observable is reduced as much as the theory allows. But this sharpness often comes at a cost, because other related observables may become less definite. Quantum theory constantly balances certainty in one place with openness in another. Precision tests of quantum electrodynamics using trapped particles are among the strongest agreement checks ever found between theory and experiment. The calculations in this theory are extraordinarily demanding, but when they are carried out and compared with careful measurements, the match is astonishing. This is one reason quantum electrodynamics is often seen as one of the great successes of modern physics. The antimatter partner of the electron is the positron, which has the same mass as an electron but the opposite electric charge. This was one of the most striking predictions of relativistic quantum theory. It showed that the equations did not merely describe known matter more accurately. They also pointed toward entirely new forms of matter that were later observed in the real world. CERN Antiproton Decelerator is designed to slow antiprotons down, so scientists can study them carefully, instead of only smashing them at high energies. Slowing them matters because delicate experiments require control, not just impact. At very high speed, particles reveal one kind of information. At low speed, trapped and guided, they reveal another. This is a fine example of how quantum research depends as much on patience and control as on raw power. Antihydrogen is created by combining an antiproton with a positron, making it the antimatter counterpart of ordinary hydrogen. That makes it especially valuable because hydrogen is one of the best understood systems in all of physics. By comparing hydrogen with antihydrogen, researchers can look for even the tiniest differences and test whether the laws of physics treat matter and antimatter in exactly the same way. Measurements have shown that antihydrogen is electrically neutral to extremely high precision. That matters because any detectable mismatch would hint at new physics beyond current theory. Neutrality may sound like a simple property, but when measured with enough care, even such a basic trait becomes a sensitive test of our deepest assumptions. Researchers have also measured quantum energy structure effects in antihydrogen, extending the methods of spectroscopy into antimatter. Spectroscopy studies the internal energy levels of systems by seeing how they absorb or emit radiation. Bringing that technique to antihydrogen means antimatter is no longer just something produced and noticed. It can now be examined with the same refined tools used in precision atomic physics. Antihydrogen atoms can be held in magnetic traps even though they carry no overall electric charge. This works because they still possess magnetic properties that respond to carefully arranged fields. The ability to trap them is essential because a freely moving antihydrogen atom would quickly hit ordinary matter and annihilate. Trapping creates a protected space in which quiet measurements become possible. Quantum chromodynamics is the theory that describes how quarks and gluons interact. It is the quantum theory of the strong force, one of the basic interactions of nature. Unlike electromagnetism, which often allows charged particles to move freely, the strong force has the remarkable feature of confining quarks. This makes the theory both powerful and mathematically challenging. Atomic clocks rely on specific quantum transitions inside atoms or ions, because those transitions occur at highly stable frequencies. Stability is everything in precise timekeeping. A clock is only as good as the repeatability of its internal rhythm, and quantum transitions provide rhythms of extraordinary consistency. That is why atomic clocks have become the standard for the finest measurements of time. Quantum logic spectroscopy uses the motion shared by trapped ions to transfer information from a hard-to-read ion to one that can be measured more easily. This is a delicate and clever method. One ion acts almost like a messenger, carrying information across a quantum link. It allows researchers to study species that would otherwise be too difficult to probe directly. The hydrogen maser uses stimulated emission in hydrogen to generate a very stable microwave signal. In this sense, it is a close cousin of the laser, but working at a lower frequency range. Its stability makes it valuable for precision measurement and timing, and it shows how a well-chosen quantum transition can become the heart of a highly reliable instrument. Quantum spectroscopy can reveal minute shifts in energy levels caused by magnetic fields, electric fields, motion, or even relativistic effects. These shifts may be tiny, but they carry important information. By reading those changes carefully, scientists can learn about the environment surrounding the system or test deeper aspects of physical theory with very high sensitivity. The narrower an atomic transition line is, the better it serves as a reference, because a narrow line means the energy difference is very sharply defined. A broad line contains more uncertainty, while a narrow one acts like a cleaner and more precise marker. In measurement science, this difference can be crucial, which is why so much effort goes into isolating systems and reducing noise. Atomic recoil from absorbing or emitting a photon is very small, but in precision experiments, it cannot be ignored. When an atom takes in a photon, it also receives a tiny kick in momentum. When it emits one, there is another kick. These effects are subtle, yet at the highest levels of precision, even such small changes influence the outcome and must be included. Josephson predicted that Cooper pairs could tunnel across a thin, insulating barrier between two superconductors. This is a delicate quantum effect because the particles involved do not cross in the ordinary classical way. Instead, the paired electrons maintain a coherent quantum relationship across the barrier. The effect revealed how tunneling can operate not just for isolated particles, but for collective quantum states. That tunneling current can flow with zero voltage, which is one of the defining signatures of the Josephson effect. In normal thinking, current flow is usually tied to an applied voltage. Here, the quantum coherence of the superconducting state changes the picture. It allows a current to pass through the junction in a way that feels almost impossible from a classical point of view. Josephson junctions can convert frequency into voltage with extraordinary exactness. Because of this, they are used in precision voltage standards. What makes them so special is that their behavior is tied directly to fundamental quantum relations, which makes them dependable in a very deep way. Instead of relying on imperfect material artifacts, the measurement can rest on a reproducible quantum effect. Programmable Josephson arrays can generate highly precise alternating current waveforms, as well as direct current standards. This extends the usefulness of the Josephson effect beyond a single fixed measurement task. By arranging many junctions together and controlling them carefully, researchers can build practical systems that turn an elegant quantum principle into a flexible measurement tool. A SQUID, or superconducting quantum interference device, uses Josephson junctions to detect extraordinarily small magnetic signals. It is one of the most sensitive magnetic sensors ever developed. The reason it works so well is that quantum interference in the superconducting circuit responds with great delicacy to changes in magnetic flux. Tiny differences that would be invisible to ordinary instruments can become measurable. The quantum Hall effect appears when electrons are restricted to move in a flat layer at very low temperatures under a strong magnetic field. In those conditions, the motion of the electrons becomes quantized in a very particular way. The result is not just another electrical effect. It is a deeply quantum phenomenon that reveals precise and robust structure in the behavior of charge. In the integer quantum Hall effect, the Hall conductance changes in exact steps instead of varying smoothly. This stair-step behavior is remarkable because it shows that under the right conditions, electrical response becomes locked to discrete quantum values. The precision of those values is one reason the effect became so important in metrology. Those quantum Hall plateaus are so exact that the effect became a foundation for resistance standards. This is one of the clearest examples of a strange low-temperature quantum phenomenon becoming a practical reference for measurement science. The reliability comes from the fact that the effect is tied to fundamental quantities. not to the imperfections of any one sample. The fractional quantum Hall effect revealed a very different kind of quantum state, one created by strongly interacting electrons acting together. Here, the electrons cannot be understood as mostly independent particles. Their collective behavior produces a new type of quantum fluid whose properties are richer than the sum of its parts. In the fractional effect, electrons behave collectively rather than almost independently. This matters because it shows how quantum systems can reorganize themselves into entirely new forms when interactions become strong enough. The individual particles are still present, but the most useful description is no longer about separate electrons. It is about the emergent whole they form together. The fractional quantum Hall effect led to the idea of quasi-particles carrying fractional electric charge. This is startling because electric charge is often introduced as if it comes only in familiar fixed units. Yet inside this unusual many-electron system, excitations can behave as though they carry only part of that usual amount. It is a reminder that collective quantum systems can produce properties that seem impossible at first glance. Those fractionally charged excitations are not fundamental particles roaming empty space on their own. They are emergent features of a highly organized many-electron system. That distinction is important. Quantum matter can produce excitations that behave like particles, even though they exist only within a specific material environment. Berry phase is a quantum phase that depends on the geometry of a system's evolution, not only on how long the system evolves. This means that the path taken through a space of possible states can matter in a deep way. Quantum theory is not only about energies and forces. It is also sensitive to shape, structure, and geometry in a very refined mathematical sense. Geometric phases help explain a variety of condensed matter phenomena, including parts of topological band theory. They are subtle because nothing obvious may change in the local appearance of the system, yet the accumulated phase can still influence measurable outcomes. This is one of the beautiful, quieter aspects of quantum physics. Invisible mathematical structure can leave clear physical fingerprints. Light-emitting diodes work because electrons and holes recombine across a semiconductor bandgap and release photons. That process is quantum at its core. The allowed energy structure of the material determines what photons can be emitted, which is why different semiconductor systems can produce different colors of light. In stimulated emission, an incoming photon can trigger an excited atom or similar emitter to release another photon that matches it. The emitted photon shares the same energy and phase relationship, which is why this process is so important for coherent light sources. It allows light to build up in an orderly way rather than as a random glow. Laser light is unusually coherent because many photons are produced in the same mode with closely related phase and frequency. This coherence is what makes lasers so distinct from ordinary light bulbs or flames. The light is not just bright. It is highly organized, which gives it the sharpness and controllability used in science, medicine, and technology. Quantum dots are nanostructures so small that the charge carriers inside them have discrete energy levels rather than the broader bands seen in larger materials. In a sense, shrinking the system forces the quantum nature of the particles to stand out more clearly. Their small size turns them into controllable miniature quantum emitters. Because the energy levels of a quantum dot depend on its size, changing the size changes the color of light it can emit. This is a vivid example of quantum confinement. A purely geometric change at the nanoscale leads directly to a change in optical behavior, allowing engineers to tune properties by adjusting dimensions. A quantum dot can emit a single photon at a time, which is especially valuable for quantum communication. Ordinary light sources often produce uncertain numbers of photons, but some quantum tasks require far tighter control. A source that reliably emits one photon per event becomes a very useful building block for secure communication and other quantum technologies. Single photon sources matter because many quantum protocols depend on knowing exactly how many quanta are involved. If a pulse unexpectedly contains more than one photon, it can weaken security or degrade performance. A carefully engineered single photon source therefore provides a cleaner and more trustworthy quantum signal. Scanning tunneling microscopes rely on quantum tunneling between a sharp tip and a surface. The tip does not need to crash into the sample to gather information. Instead, when brought extremely close, electrons can tunnel across the tiny gap. Measuring that tunneling current gives access to the surface at a remarkable level of detail. Because tunneling current depends extremely strongly on distance, a scanning tunneling microscope can resolve structures at nearly atomic scales. A very tiny change in the tip's position leads to a measurable change in current. That extreme sensitivity is what turns a subtle quantum effect into a powerful imaging method. A scanning tunneling microscope does not image by ordinary reflection or contact. It measures tunneling current as the tip moves just above the surface. This means the image is built from a map of quantum interaction, not from a conventional optical picture. The result is a window into structure that would be far beyond ordinary microscopes. Some low-temperature scanning tunneling studies can probe superconductors and other quantum materials in extraordinary detail. Cooling helps reduce thermal noise and preserve the delicate states researchers want to investigate. With enough control, the microscope becomes a way to explore not just shape, but the local quantum behavior of a material. Single electron devices exploit the fact that moving one electron at a time can matter in nanoscale circuits. At larger scales, individual electrons blur together into continuous current. At very small scales, the discrete character of charge becomes important, and engineers can design devices that make use of that granularity. Electron pumps are devices that can move electrons one by one with very low error rates. This makes them attractive for precision electrical standards and for understanding charge transport at the smallest controlled scale. They show that current can be treated not only as a smooth flow, but as a carefully counted sequence of individual charges. Counting individual electrons is part of a broader effort to tie electrical standards directly to fundamental quantum effects. Instead of relying on approximate material devices alone, scientists aim to define measurements through exact properties of nature. In that effort, single electron control becomes a bridge between abstract constants and practical metrology. Rotating a Bose-Einstein condensate can create quantized vortices instead of arbitrary swirling motion. In an ordinary fluid, rotation can take many forms, but in a condensate, the circulation is constrained by the quantum state. The result is a set of discrete vortex structures that reveal the underlying coherence of the whole system. The circulation around those vortices is quantized because the condensate wave function has to join up with itself consistently. The quantum phase cannot vary in just any way. It must satisfy a global condition, and that requirement forces the rotational behavior into discrete amounts. Once again, continuity at the large scale gives way to quantization underneath. Magnons are quantum excitations of spin waves in magnetic materials, and under some conditions, they can form Bose-Einstein-like condensates. This is fascinating because it shows that condensation is not limited only to familiar atoms. Other collective excitations can also organize into coherent quantum states when the right conditions are created. Entangled photons have become major tools in modern quantum information experiments because they are relatively easy to produce, guide, and detect compared with many other entangled systems. Light is naturally suited to transmission, and photons interact only weakly with the environment. That makes them ideal messengers for studying entanglement and building quantum communication methods. A qubit differs from an ordinary bit because it can exist in a superposition of logical 0 and 1 before measurement. A classical bit is firmly one or the other. A qubit, by contrast, can carry a richer state that includes both possibilities in a controlled quantum combination. This expanded state space is one of the main reasons quantum information processing is so powerful. Measuring a qubit gives a classical result, but the probabilities of those results depend on the amplitudes in the state before measurement. So the quantum richness is not seen directly as a fuzzy answer. It shows up in the pattern of outcomes across repeated trials. That is why preparation, control, and interference matter so much in quantum information science. Two qubits can display correlations that do not have a full classical equivalent once they become entangled. If you describe each qubit separately, you miss part of the real structure of the system. The pair has to be treated as one shared quantum object, in an important sense. This is one of the reasons quantum information can do things that ordinary information cannot easily imitate. Interference is central to quantum computing because useful algorithms often work by strengthening the amplitudes of wanted outcomes while weakening unwanted ones. A quantum computer does not simply try every answer in a magical way and then read them all out at once. Instead, it carefully guides the wave-like structure of probability so that the right answer becomes more likely when measurement finally happens. Quantum computers are not automatically better at every task. Their power appears only for certain problems where superposition, interference, and entanglement can be organized in a helpful way. This is important because it keeps expectations realistic. Quantum advantage is not about replacing all classical computing, but about opening a new route for problems that fit the strengths of quantum systems. Trapped ions are a leading qubit platform because they combine long coherence times with very accurate control. A single ion can be held in an electromagnetic trap, manipulated with lasers or fields, and measured with extraordinary precision. This makes trapped ions especially attractive for experiments where reliability matters more than sheer scale. They show how a very small and very controlled system can become a serious computing platform. Superconducting circuits are another major qubit platform, and they are remarkable because they show quantum behavior in devices large enough to be engineered on chips. These circuits are not microscopic particles in the usual sense. They are human-made electrical systems that, under the right low-temperature conditions, display quantized energies and coherent quantum dynamics. They prove that quantum physics can survive inside carefully designed hardware. The 2025 Nobel Prize in Physics recognized macroscopic quantum tunneling and energy quantization in an electrical circuit. That recognition highlighted something profound. Quantum behavior is not limited only to isolated atoms and electrons. Under the right conditions, larger engineered systems can also show unmistakably quantum effects. This broadens our sense of where the quantum world begins and ends. Quantum circuits can be designed so that their allowed energies are discrete, much like the energy levels of atoms. This is why people sometimes speak of artificial atoms in the context of superconducting devices. The system is built from circuit elements rather than from a nucleus and electrons, yet it still displays quantized structure. That makes it possible to borrow ideas from atomic physics and apply them to engineered electronics. Superconducting qubits rely on Josephson junctions because those junctions provide strong nonlinearity with relatively low dissipation. The nonlinearity is crucial because it separates one energy transition from another, making the device controllable as a qubit rather than as a simple harmonic system. In practical terms, the Josephson junction gives the circuit just enough individuality to act like a quantum two-level system. Quantum error correction is needed because quantum information is extremely fragile. Noise, unwanted interactions, and imperfect control can all damage the state of a qubit. Unlike classical information, Quantum information cannot simply be read out and copied over and over without changing it. So error correction in the quantum case has to be more subtle and more carefully designed. The no-cloning principle says that an unknown quantum state cannot be copied perfectly. This is not just a technical limitation of current machines. It is built into the structure of quantum theory itself. That makes quantum information fundamentally different from classical information, where copying a bit pattern is usually easy. In the quantum world, preservation and protection take the place of simple duplication. Quantum teleportation transfers a quantum state by combining entanglement with ordinary classical communication. The original particle does not fly across space in a magical way, and matter itself is not transported. What moves is the exact quantum state, reconstructed elsewhere through a protocol that depends on both shared entanglement and a classical message. It is one of the clearest examples of quantum information as a real resource. Teleportation does not beat the speed of light because the classical communication step is unavoidable. Even though entanglement provides the special link between the systems, the final reconstruction cannot be completed without ordinary information being sent through normal channels. This keeps the protocol consistent with relativity, while still making use of genuinely quantum effects. Quantum key distribution uses quantum measurements to reveal whether an eavesdropper has disturbed a signal. This is possible because measurement in quantum physics is not passive. Looking at a quantum carrier generally changes it. That feature, which might sound inconvenient, becomes a security advantage. It allows communication protocols that can detect interference in principle rather than only hoping encryption stays unbroken. Single photons are attractive carriers for quantum communication because they interact only weakly with the environment during transmission. That helps preserve the delicate quantum properties they carry. They can move through optical systems and fibers with relatively little disturbance compared with many matter-based systems. This makes them especially useful as messengers in quantum networks. Photon loss, detector noise, and decoherence are among the main challenges for long-distance quantum communication. If too many photons disappear, the signal weakens. If detectors create false counts or miss real ones, reliability drops. If coherence is lost, the quantum advantage disappears. The promise of quantum networking therefore depends not only on elegant theory, but on solving many practical physical problems. Quantum repeaters are proposed devices meant to extend entanglement over long distances. Instead of trying to send one fragile quantum signal all the way across a huge span at once, the idea is to build the connection in smaller sections and then link them together. This is important because direct transmission becomes increasingly difficult as distance grows. Quantum dots are being developed as spin-photon interfaces for future repeater systems. That means they may be able to connect stationary quantum information, such as a spin state, with flying quantum information carried by light. Such interfaces are valuable because a useful network often needs both memory and transmission, not just one or the other. Integrated quantum photonics aims to place multiple quantum optical functions onto a single chip. Rather than building every element as a separate bulky component, researchers want sources, waveguides, detectors, and control structures all combined in compact hardware. This approach could make quantum devices smaller, more stable, and easier to scale. On-chip quantum photonics can combine light sources, waveguides, and detectors in one compact architecture. This matters because alignment problems and instability often grow when systems are spread out. Bringing the pieces together on one chip can reduce that complexity. It is a way of translating delicate laboratory optics into something more robust and practical. Efficient single-photon detectors are essential because many quantum communication protocols fail if photons are lost without being noticed. A missed photon can mean lost information, broken correlations, or reduced security. So detection efficiency is not just a performance statistic. It is often central to whether a quantum protocol works reliably at all. Transition-edge sensors can detect single photons with extremely high efficiency by operating near the boundary between superconducting and normal behavior. In that narrow region, tiny energy inputs produce measurable changes. This makes the device extraordinarily sensitive. It is an example of how quantum and low-temperature physics can be turned into powerful instrumentation. Superconducting nanowire single-photon detectors are highly valued for their efficiency, low noise, and fast response. They are especially useful in modern quantum optics because they can register faint signals with very little added disturbance. When experiments depend on counting single photons accurately, these detectors often become key pieces of the whole system. Telecom band quantum technologies matter because existing fiber networks are optimized for those wavelengths. If quantum communication can operate where modern infrastructure already performs best, it becomes easier to connect new quantum tools to current communication systems. This is one case where the path toward the future is helped by compatibility with what already exists. Quantum communication in space is being explored because satellites can bridge distances that are difficult to cover in fiber alone. Over very long spans, fiber losses become a major problem. Space-based links offer another route, potentially allowing quantum states or keys to be shared over global scales with fewer intermediate losses. Quantum simulators can help study systems that are too difficult to calculate exactly on ordinary computers. Instead of solving every equation directly, researchers build a controllable quantum system that follows similar rules. Then they observe how it behaves. This makes the simulator a physical stand-in for a problem that may be mathematically overwhelming in full detail. Not every quantum simulator is a universal quantum computer. Many are designed for a particular class of systems or interactions. That narrower purpose can actually be an advantage because focusing on one problem family may allow better control and more efficient use of the hardware. Specialized tools often become powerful precisely because they are not trying to do everything. The usefulness of a qubit platform depends on more than coherence time alone. Connectivity, date accuracy, readout quality, speed, and manufacturability all matter. A qubit can be beautifully stable and still be hard to build into a larger machine. So evaluating a platform means balancing many strengths and weaknesses at once. Quantum control often uses carefully timed pulses that rotate states in an abstract state space instead of moving a visible object through ordinary space. This can feel unintuitive at first. The language of rotation remains, but what rotates is the relationship between possible states, not a little ball turning in front of us. Quantum control is therefore both physical and deeply mathematical. Quantum readout is itself a difficult engineering problem because extracting information can damage the state you hope to preserve. Measure too weakly and you may not learn enough. Measure too strongly or at the wrong moment and you may destroy the coherence needed for the next step. This balance makes readout one of the central challenges in quantum technology. Much of modern quantum technology comes down to deciding when a system should stay isolated and when it should interact. Isolation helps preserve coherence. Interaction allows control, coupling, and measurement. A successful device must move between these two needs gracefully, protecting the quantum state at one moment and deliberately touching it at another. Decoherence is often caused by unwanted entanglement with the environment. When a system leaks phase information into surrounding degrees of freedom, the clean relationships inside the quantum state begin to break down. The system does not stop existing, but its useful quantum character fades. This is one of the main reasons large-scale quantum control is hard. Thermal motion is a frequent enemy of coherence because it introduces fluctuating interactions that scramble delicate phase relationships. Heat is not just warmth in the ordinary sense. At the microscopic level, it often means restless motion and uncontrolled influence. Cooling, therefore, becomes one of the most important tools for preserving fragile quantum behavior. Shielding, cooling, and vacuum systems are common defenses against environmental noise in quantum experiments. Each one removes a different kind of unwanted disturbance. Shielding reduces stray fields. Cooling reduces thermal agitation. Vacuum reduces collisions with surrounding particles. Together, they create the quiet conditions that sensitive quantum systems need. Quantum measurement back action means that observing a system can physically disturb it. In classical thinking, we often imagine that measurement simply reveals what was already there. In quantum mechanics, the act of measurement is part of the physical process. What we choose to measure and how we measure it can reshape the state itself. In weak measurements, the disturbance can be reduced, but the information gained from each individual attempt is also limited. This trade-off is very characteristic of quantum physics. Gentler probing usually means less disruption, but also less certainty in a single shot. To learn more, many repeated trials are often needed. The quantum Zeno effect is the slowing or suppression of evolution through sufficiently frequent observation or projection. In a rough, intuitive picture, repeatedly checking the system can keep it from changing in the way it otherwise would. This is a striking example of measurement doing more than reporting a process. It can influence the process itself. The Zeno effect shows that measurement in quantum mechanics can actively reshape dynamics. Observation is not merely an outside commentary on what the system is doing. It becomes part of the system's story. This gives quantum measurement a more participatory role than most classical intuitions would suggest. Quantum eraser experiments show that interference can depend on whether which path information is available. If the setup allows path information to exist in principle, interference can disappear. If that information is removed from the relevant description, interference can return in the processed results. These experiments do not erase the past, but they do reveal how deeply information and interference are linked. Double-slit experiments remain central in quantum physics because they expose amplitude, phase, and information in one elegant setup. A particle-like detection pattern builds up from many individual events, yet the full distribution reflects wave-like interference. The experiment is simple to describe and endlessly deep in what it teaches. A system can look wave-like in one experiment and particle-like in another because different setups test different aspects of the same quantum object. This is not a contradiction in the theory. It is a sign that our ordinary classical pictures are incomplete. The experimental arrangement matters because it determines which features become visible. Quantum states can be pure or mixed. A pure state represents a more complete quantum description, while a mixed state describes either incomplete knowledge or a system that is entangled with surroundings we are not tracking. This distinction is important because real experiments often deal with mixtures, not perfect textbook purity. Density matrices are useful because they describe both pure states and mixed states within one framework. They extend the language of quantum mechanics so that uncertainty, noise, and partial information can all be handled consistently. In practice, they are essential for real-world quantum systems, where perfect isolation is rare. Entanglement entropy is one way to measure how strongly a subsystem is linked to the rest of a larger quantum system. If the entropy is high, the subsystem cannot be fully understood on its own. This concept has become important in many areas, from quantum information to condensed matter theory, because it gives a quantitative way to describe quantum interconnectedness. Quantum phase transitions can occur even at zero temperature when a changing control parameter alters the ground state of the system. Unlike ordinary phase changes driven by heating or cooling, This kind of transition is driven by quantum fluctuations and competing interactions. It shows that even in the absence of thermal agitation, matter can reorganize itself dramatically. Unlike ordinary thermal phase transitions, a quantum phase transition is not primarily driven by heat. It is driven by the quantum structure of the ground state itself. This makes it a more subtle kind of change, yet one that can have large and observable consequences for the material or system involved. Critical quantum systems often display collective behavior across many length scales. Near the transition point, details from the very small and the much larger can become linked in unusual ways. This scale-spanning behavior is one reason critical phenomena remain so important and so mathematically rich. Some quantum phases are characterized by topological invariants, which are discrete mathematical quantities that do not change under smooth deformation. This means the important feature is not a local bump or detail, but a broader structural property of the whole system. Such invariants help explain why certain physical responses can remain robust even when materials are imperfect. Because topological quantities are discrete, they can protect physical behavior against many small disturbances. Tiny defects or irregularities may not matter as much as they would in more ordinary phases. This robustness is part of what makes topological matter so interesting for both fundamental science and possible applications. Quantum fluids can host collective excitations that behave like new particles with properties different from the atoms or electrons that produced them. These excitations are real in the sense that they can be measured and can carry energy, momentum, or charge-like behavior. Yet they are emergent rather than fundamental, arising from the organized motion of many constituents. A quasi-particle is not a fake particle. It is a real, measurable excitation inside a material or medium. The word simply reflects that it is not an elementary particle of empty space. Quantum many-body systems often become easier to understand when their collective behavior is described in terms of quasi-particles. Exchange statistics in 2 dimensions can be richer than the simple Bosanoff-Fermion split familiar from 3-dimensional particles. This means that in certain systems, exchanging 2 excitations can lead to more exotic mathematical behavior. The possibilities broaden, and with them our understanding of how quantum identity can work. Fractional quantum Hall systems are among the main places where especially unusual collective excitations are studied. These systems provide a natural laboratory for exploring strongly correlated behavior, fractional charge, and unusual exchange properties. They continue to be one of the most fertile grounds for discovering new kinds of quantum organization. Quantum geometry has become increasingly important for understanding some flat-band and multiband systems. Here, the arrangement of quantum states in an abstract space influences measurable properties of materials. Once again, geometry in quantum physics is not merely a decorative mathematical idea. It can shape real physical behavior. Even when a system is in its ground state, quantum theory may still predict fluctuations because zero-point motion does not disappear completely. The lowest energy state is not always a perfectly motionless one. This is one of the quiet but profound differences between classical and quantum thinking. The floor of activity is not absolute stillness. Zero-point effects matter in precision mechanics, optics, and low-temperature experiments, because once other noise sources are reduced enough, this baseline quantum activity remains. What would once have been hidden becomes important. As measurement grows more refined, the subtle motion built into the ground state can no longer be ignored. Quantum noise can sometimes be redistributed rather than simply removed, and this is the basic idea behind squeezing. Instead of making all uncertainty smaller at once, which quantum theory forbids, one can reduce uncertainty in one variable while allowing it to grow in its conjugate partner. This is a powerful way of improving performance for specific measurement tasks. A squeezed state reduces uncertainty in one quantity at the cost of increasing it in the corresponding conjugate quantity. The total quantum constraint remains in place, but the balance changes. This makes squeezing especially useful when one variable matters more than the other for a particular experiment. This trade-off still fully obeys the uncertainty principle. Squeezing does not beat quantum mechanics. It works within quantum mechanics by rearranging uncertainty in a helpful way. That is why it has become such an important technique in precision measurement. Quantum foundations remain an active area of thought because the theory works with astonishing success while still allowing different interpretations of what the mathematics means. Physicists may disagree about the best philosophical picture, but they do not disagree that the equations predict experiments with extraordinary accuracy. This creates a rare situation in science, a framework that is deeply successful in practice and still rich in conceptual mystery. Whichever interpretation a person prefers, the laboratory predictions of standard quantum mechanics remain the benchmark that experiments continue to confirm. That matters because science is ultimately grounded in what nature does, not only in the stories we tell about it. Interpretations may vary, but the measured outcomes keep returning to the same dependable mathematical core. GPS and similar navigation systems rely on atomic clock technology, which means quantum physics quietly supports everyday navigation across the modern world. When someone checks a map, follows a driving route, or tracks a delivery, they are depending on clocks whose precision comes from quantum transitions in atoms. The microscopic world, in this case, helps organize the large-scale movement of people and machines. Medical imaging and therapy also make use of tools sharpened by particle and quantum physics. Devices for detecting radiation, producing beams, and measuring delicate signals were shaped by research into matter at its deepest levels. This is a good example of how knowledge that begins in fundamental science often returns in practical forms that support health and medicine. Semiconductor electronics depend fundamentally on quantum band structure, tunneling, and the statistical behavior of charge carriers. Modern computing, communication, and countless everyday devices rest on materials whose behavior cannot be understood fully without quantum theory. Even when a phone or computer feels ordinary, its operation is built on subtle microscopic rules. Lasers are used in communication, manufacturing, medicine, and research because they rely on a controlled quantum emission process. Their usefulness comes from coherence, precision, and intensity that ordinary light sources cannot easily provide. In this way, a once strange quantum concept became one of the most versatile tools in modern technology. MRI depends on quantum properties of atomic nuclei, especially spin and resonance. In a strong magnetic field, certain nuclei respond in ways that can be measured and turned into detailed internal images of the human body. So even advanced medical scans are, in an important sense, reading out the quiet quantum behavior of matter. PET scans use antimatter indirectly by detecting the photons produced when positrons meet electrons and annihilate. This means a process that might seem exotic and remote from daily life is actually part of routine medical imaging in many places. Antimatter in this setting is not science fiction. It is part of a practical method for seeing processes inside the body. Quantum standards are increasingly valuable in metrology because they connect measurements to fundamental constants rather than to fragile physical artifacts. This makes standards more stable, more universal, and less dependent on any one material object. It is a major shift in how precision is anchored, moving from man-made reference pieces toward nature's own rules. Resistance can be standardized using the quantum Hall effect. Because the relevant electrical values appear in precise quantum plateaus, they provide an exceptionally reliable reference. This is one of the clearest examples of a delicate low-temperature quantum phenomenon becoming part of the practical foundation of measurement science. Voltage can be standardized using Josephson junctions. Their behavior ties electrical measurements directly to exact quantum relationships between frequency and voltage. This gives voltage standards a remarkable level of reproducibility and shows again how quantum effects can be turned into dependable tools. There are also efforts to build standards by counting individual electrons, linking charge and current directed to the elementary charge itself. This approach treats electrical flow not just as something smooth, but as something made from countable, discrete units. It reflects the same quantum spirit seen elsewhere in metrology. Use the most fundamental structure possible. Single photon detectors with very high efficiency are helping turn quantum optics from a delicate laboratory exercise into something more robust and practical. When the ability to notice a single quantum of light becomes reliable enough, many protocols move from fragile demonstrations toward usable technologies. Better detection often changes the entire field around it. Quantum sensors can measure time, motion, gravity, magnetic fields, and photons, with sensitivities that classical methods often struggle to match. Their power comes from using coherence, quantization, and interference as resources rather than nuisances. In a broad sense, they are instruments that listen to the world through quantum behavior. Space missions are attractive testbeds for quantum sensors because they offer long freefall times, large gravitational differences, and in some cases, reduced environmental disturbance. These conditions can help certain measurements reach higher sensitivity than they would on Earth. Space then becomes not only a destination for exploration, but also a laboratory for refined quantum measurement. Quantum communication research is not mainly about making ordinary messages travel faster. Its deeper goal is to improve security and to create networks in which quantum states themselves can be distributed or shared. That makes it a different kind of communication science, one focused on the character of information itself. Chip-scale photonic integration may allow quantum hardware to become more compact, stable, and manufacturable. Large optical tables full of separate components are powerful, but they are not always practical. By shrinking many functions onto chips, researchers hope to make quantum devices more robust and easier to reproduce. Some quantum devices use cryogenic temperatures not because coldness is fashionable, but because thermal noise would otherwise overwhelm the states they depend on. Heat introduces disorder, motion, and random interactions. Cooling reduces that restless background and gives fragile quantum behavior a better chance to survive long enough to be useful. Superconducting detector arrays are being used in areas ranging from astrophysics to X-ray microanalysis. These systems show how quantum materials can serve not only as subjects of study, but as tools for gathering information from the wider universe and from fine material structure. A quantum device can become the eye of another science. Quantum dots and nanophotonic structures are being designed to make light sources brighter, purer, and easier to connect into circuits. This is important because controlled light generation and delivery are central to many emerging quantum technologies. Tiny structures, carefully engineered, can strongly shape how quantum light is produced and guided. The first quantum revolution produced technologies such as semiconductors and lasers by learning how to understand quantum matter. The second quantum revolution focuses more on directly controlling coherence and entanglement. This distinction helps explain why today's quantum technologies feel different. They are not just using quantum effects passively, but actively shaping them. That difference also shows how a scientific theory can mature over time. First, it explains the world well enough to build practical devices. Later, it becomes precise enough to engineer new kinds of systems around its deepest features. Quantum theory has moved from explanation toward deliberate design. LIGO must cope with quantum noise because even vacuum fluctuations matter when the signal being measured is unimaginably small. the detector is trying to sense tiny distortions in space-time itself, and at that level, even the quantum character of light becomes relevant. This is a powerful reminder that quantum physics reaches into the edge of what humans can measure. Squeezed light has been added to gravitational wave detectors to improve sensitivity. By redistributing uncertainty in a way helpful for the measurement, researchers can reduce the noise that matters most. This is a beautiful example of quantum ideas being used not only to understand nature, but to extend the reach of observation itself. LIGO frequency-dependent squeezing uses a long filter cavity so that the noise reduction can help across a broad band of frequencies. This is a sophisticated refinement of the squeezing idea, showing how subtle quantum engineering can be adapted to the needs of a real instrument. It is not enough to reduce noise in one narrow place. The reduction has to match the detector's full task. In 2023, LIGO reported sensitivity gains that surpassed the standard quantum limit across its full detected gravitational wave band. That achievement matters because the standard quantum limit was once treated as a fundamental boundary for certain measurements. Reaching beyond it in practice shows how far careful quantum control has advanced. This is a striking example of quantum engineering helping measure a phenomenon predicted by general relativity. One theory of the very small helps sharpen our ability to observe one theory of the very large. There is something deeply satisfying in that meeting, different parts of physics supporting one another in the same instrument. Quantum photonic circuits may eventually support communication, sensing, and information processing on shared optical platforms. If successful, they could bring several quantum functions into compact and integrated systems. That would make the technology more flexible and could help different quantum applications grow together rather than separately. Quantum hardware often advances through better materials science as much as through better abstract theory. A brilliant equation is not enough if the materials introduce too much loss, noise, or disorder. The history of the field shows again and again that cleaner materials and better fabrication can unlock effects that theory already anticipated. Improvements in fabrication, vacuum technology, cryogenics, and control electronics are often what turn a fascinating quantum effect into something genuinely usable. In many cases, the leap from laboratory curiosity to practical tool does not come from a new concept alone. It comes from learning how to protect and shape the conditions the concept needs. Quantum physics is therefore not only a set of equations about the microscopic world, it is also a foundation for engineering, standards, instrumentation, and the design of new technologies. The theory has grown into a toolkit for building some of the most exact devices humans have ever created. Many of the most precise tools ever built are precise precisely because they are anchored to quantum behavior. Their stability comes from the repeatable structure of atoms, fields, and quantum effects, rather than from rough mechanical reference points. Quantum regularity has become a practical resource. Macroscopic quantum effects are no longer limited to thought experiments. They are observed in superconducting circuits, condensates, and precision interferometers. This matters because it expands our imagination of where quantum behavior can live. Under the right conditions, large engineered or collective systems can reveal the same deep principles first noticed in microscopic particles. The fact that hand-sized electrical circuits can display quantum tunneling shows that quantum behavior is not restricted only to tiny isolated particles. What matters is not simple physical size alone, but whether coherence and quantized behavior can be preserved. This opens a broader view of the quantum world as something that can be engineered rather than merely found. Quantum behavior in larger systems is harder to preserve mainly because large systems couple more easily to their surroundings. More connections mean more chances for noise, loss, and decoherence. This is why scaling up quantum devices is so demanding. The difficulty is not only in making something larger, but in keeping it quiet while it grows. Some of the best present-day quantum experiments work by carving out tiny protected islands of coherence inside much larger ordinary machines. A cryostat, a vacuum chamber, a filtered circuit, or a carefully isolated optical path becomes a quiet refuge where the quantum state can survive. This image captures much of modern quantum engineering. Small pockets of delicate order sheltered inside a noisy world. Antimatter spectroscopy matters because even the tiniest difference between hydrogen and antihydrogen could point to new physics. Since hydrogen is one of the best understood systems in science, comparing it with its antimatter twin becomes a powerful test. If a mismatch ever appeared, it could reveal a crack in our current understanding. Increasing the production rate of antihydrogen helps experiments gather meaningful data more quickly. Precision studies depend not only on quality, but also on enough events to build confidence. When antimatter is difficult to produce and trap, every improvement in rate expands the practical reach of the science. Trapped antihydrogen has now been held long enough for researchers to test its charge neutrality, internal structure, laser cooling behavior, and gravity-related properties. That is a major shift from simply proving antimatter exists. It means antimatter has entered the era of detailed, methodical measurement. Quantum studies of antimatter depend on slowing particles down, because fast antimatter annihilates too quickly to examine carefully. High-energy production is good for discovery, but low-energy control is what allows fine tests. This balance between making particles and taming them is one of the great themes of experimental physics. The ability to cool and trap increasingly exotic systems has become a recurring theme in modern quantum physics. From ordinary atoms to ions to antimatter, control often begins by reducing motion and isolating the system. Cooling does not just make things colder. It creates the calm conditions where subtle structure can finally be studied. Quantum simulations are now being explored for high-energy physics questions, as well as for condensed matter and chemistry. This expansion shows that simulation is becoming a more general strategy for tackling complex quantum problems. Instead of solving everything only with paper mathematics, researchers are increasingly willing to let one quantum system illuminate another. One long-term goal is to study quantum systems whose complexity grows so rapidly that direct classical calculation becomes impractical. This is one of the deepest motivations behind quantum simulation and quantum computing. Nature can carry out quantum evolution directly, even when our classical descriptions become painfully difficult. Quantum matter research keeps uncovering phases that were not anticipated by older schemes based only on symmetry breaking. This means the catalogue of possible organized states of matter is richer than many earlier pictures suggested. Quantum theory continues to widen our sense of what matter can be. The discovery of topological matter showed that global mathematical structure can be physically measurable in a material. Instead of focusing only on local order, physicists learned that deeper overall organization can shape real transport and response properties. It is one of the most elegant examples of abstract mathematics becoming laboratory reality. The discovery of fractional quantum Hall states showed that electrons, which individually resist sharing the same state, can still collectively form a new kind of quantum fluid under extreme conditions. This is a powerful lesson in emergence. The rules for one particle do not always reveal what many particles together can become. Bose-Einstein condensates showed the opposite extreme. Bosons can gather into one shared ground state when cooled enough. The result is a macroscopic quantum system that behaves in a coherent collective way. It is one of the clearest demonstrations that statistics at the particle level can shape dramatic large-scale behavior. Superconductivity showed that fermions can also acquire boson-like collective behavior after pairing. Once electrons form Cooper pairs, they can participate in a coherent state that supports remarkable effects such as zero resistance. Pairing changes what is possible, turning exclusion-limited particles into part of a collective whole. Taken together, these examples reveal a deep lesson of quantum physics. The collective can behave very differently from the individual. Large, organized systems can display properties that are not obvious from studying one particle alone. This is why many-body quantum physics is so rich, and why emergence is such a central idea. Quantum theory keeps extending from explanation to control, turning once puzzling ideas into practical tools for clocks, sensors, networks, and computation. That progression is one of the quiet triumphs of modern science. What once seemed strange has become useful, without losing its depth. Even after more than a century of success, quantum physics is still expanding into new regimes such as space-based sensing, engineered topological matter, and precision antimatter studies. It is not a finished chapter. It remains a living, growing field whose frontier keeps shifting. One reason quantum physics remains so compelling is that the same framework explains atomic spectra, the behavior of solids, the structure of elementary particles, and many of the most advanced technologies now being built. Few scientific theories reach across so many scales and so many kinds of phenomena with such consistency and power. Quantum jumps between atomic energy levels are real transitions, not smooth gliding motions between every possible value. In the quantum picture, an atom is allowed to occupy specific energy states, and when it changes from one to another, the change is discrete. This can feel abrupt when compared with ordinary intuition, but it is one of the quiet rules that gives atomic physics its beautiful structure. In semiconductors, tunneling is not just an odd and rare effect. It is important enough to be the working principle behind devices such as tunnel diodes. That means a behavior that sounds almost impossible in classical physics becomes part of useful electronics once matter is arranged at the right scale and under the right conditions. Quantum tunneling can also occur in superconductors, where paired electrons cross very thin insulating barriers without ordinary electrical resistance. In this setting, tunneling is not simply about a lone particle sneaking through a wall. It is part of a larger, more coherent quantum state. That gives the effect an especially calm and elegant quality, as if the particles move together under rules that belong to the whole system. Free particles can still be described by quantum mechanics, even though their energies are not restricted in the same way as bound states in atoms. This is a helpful contrast. Atoms have a ladder of allowed energies because their particles are confined, while free particles are not tied down in that same way. Quantum theory is broad enough to describe both the trapped and the unconfined. Bosons are particles that can occupy the same quantum state in large numbers. This simple rule has surprisingly wide consequences. It is one reason collective states such as laser light and Bose-Einstein condensates are possible. Instead of being forced apart by their quantum identity, bosons can gather into a shared pattern. Fermions follow a different rule. They obey the exclusion principle and resist crowding into the same state. This gives them a more structured and layered style of behavior. The difference between bosons and fermions is one of the deepest quiet divisions in quantum physics, and many large-scale physical properties grow out of it. Electrons are fermions, and that is one reason they build layered structures in atoms and solids. They do not all settle into the same lowest arrangement. Instead, they fill available states in an orderly way, and from that ordering come atomic shells, chemical behavior, and much of the structure of matter around us. Photons are bosons, which is one reason lasers can produce large numbers of photons in the same mode. Because photons are allowed to gather into one shared optical state, laser light can become highly organized, with many quanta moving together in a remarkably orderly way. This is another example of particle identity shaping a visible technological result. Superconductors do more than simply carry current without resistance. They also expel magnetic fields in a phenomenon known as the Meissner effect. This is important because it shows superconductivity is a distinct quantum phase of matter, not merely an improved conductor. The material reorganizes itself in a deeper way. Cooper pairs behave collectively in a superconductor, giving the whole state a single coherent quantum character. Instead of thinking only about separate electrons moving independently, it becomes more accurate to think about a larger unified state. That shared coherence is what allows the superconductor to behave so differently from an ordinary metal. In a superconductor, the paired electrons move in a coordinated way that avoids the usual scattering processes responsible for electrical resistance. In normal materials, electrons are constantly disrupted by imperfections and vibrations. In the superconducting state, the collective order changes that story, allowing current to flow in a much calmer and more stable way. SQUADE are not only sensitive in a laboratory sense, they are so delicate in their magnetic response that they are useful in astronomy, X-ray detection, and other lower noise measurement systems. This shows how a refined quantum device can become a practical listening tool for faint signals that would otherwise be lost. Topological phases of matter are not defined mainly by the kind of local order we see in familiar materials, such as the alignment of a magnet. Instead, they are characterized by more global quantum properties. This means the important feature is woven through the whole system, rather than sitting in one easily visible place. Topology entered condensed matter physics, in part because scientists were trying to understand why quantum Hall behavior could be so robust. The answer was not simply about local details of the material. It involved deeper structural properties of the quantum state. That shift opened an entirely new way of classifying phases of matter. A topological quantum fluid can retain its important properties even when the material contains imperfections. This stability is one of the reasons topological matter became so interesting. The behavior is protected not by perfect cleanliness alone, but by a broader structural feature of the state itself. Topological insulators are unusual materials that conduct along their edges or surfaces while remaining insulating in the bulk. That contrast gives them a very distinctive character. The inside behaves one way, while the boundary behaves another, and the reason lies in the deeper topology of the quantum state, rather than in a simple surface coating. The quantum spin Hall effect is a related phenomenon in which opposite spin channels move in opposite directions along an edge. This gives the boundary of the material a kind of organized balance, with spin and motion linked together. It is another reminder that quantum structure can shape transport in ways that ordinary pictures would not predict. Band structure in solids arises because electron waves must fit the repeating arrangement of a crystal lattice. This means that the periodic order of the material and the wave nature of the electron work together to define what images are allowed. The familiar properties of solids are therefore rooted in a very quiet kind of quantum geometry. A material becomes a metal, semiconductor, or insulator, largely because of how its allowed electron bands are filled. This is one of the great simplifications of solid-state physics. A huge range of visible behavior can be traced back to the pattern of allowed quantum states and how electrons occupy them. Semiconductors became so useful because their band gaps can be engineered to control current and light emission. That controllability is what made modern electronics and optoelectronics possible. The success of semiconductor technology is, in a deep sense, the success of learning how to shape quantum structure inside materials. Quantum dots can be excited either optically or electrically, which gives designers flexibility when building light sources and quantum devices. Some systems use light to prepare them, while others use electrical control. This adaptability is part of what makes quantum dots such versatile tools in modern photonics. Semiconductor nanostructures can confine quantum particles in 0, 1, or 2 dimensions, creating dots, wires, and wells with very different behaviors. Changing the geometry changes the allowed states. At very small scales, shape and dimensionality are no longer minor details. They become central parts of the physics. Quantum electrical metrology makes use of effects such as Josephson voltage steps and quantum Hall resistance plateaus because these behaviors are tied to fundamental constants. That link is precious in measurement science. It means the standard does not drift with a particular object or device, but rests on something far more universal. Superfluidity is another macroscopic quantum phenomenon, one in which matter can flow with extremely low dissipation. The fluid behaves in a way that is strikingly different from ordinary liquids, showing once more that collective quantum order can express itself on a visible scale when the conditions are right. A Bose-Einstein condensate is often described as a macroscopic quantum state because a huge number of particles share one wave function-like description. Instead of acting as many separate little pieces, the particles contribute to a common state. That shared behavior gives the condensate its special stillness and coherence. Condensates in dilute gases are not the same thing as superconductors, but both involve collective quantum coherence. This comparison is helpful because it shows the same broad idea appearing in different physical settings. Quantum theory does not express coherence in only one form. It returns again and again in different materials and systems. Under suitable conditions, rapidly rotating condensates can enter regimes related to quantum Hall physics. This is a beautiful crossing point between two seemingly different areas of physics. A cold atomic gas and an electron system in a strong magnetic field can begin to echo one another in their deeper quantum organization. Bosonic systems can also show topological behavior, extending ideas that were first developed mainly for electron systems. This is an important broadening of perspective. Topology is not a private feature of one narrow family of materials. It is part of a larger quantum language that different systems can speak. Exciton condensates are collective quantum states, formed from bound electron-hole pairs in certain layered or low-dimensional systems. These states show that coherence can emerge not only from atoms or electrons alone, but from paired excitations created inside materials. Quantum matter keeps finding new ways to organize itself. Hybrid systems that combine light and matter can support collective quantum behaviors not found in either ingredient alone. This is one of the gentler lessons of modern physics. When different kinds of quantum systems are coupled carefully, the combination can become more interesting than either part on its own. Many-body quantum physics often produces emergent properties that are not obvious when studying a single particle in isolation. A lone particle may follow one set of simple rules, but a very large collection can behave in a way that feels almost like a new world. That is why quantum matter can remain surprising even when its basic ingredients are known. Some of the most surprising discoveries in solid-state physics did not come from isolated particles at all. They came from huge ensembles acting together coherently. This is a useful reminder that complexity does not always blur physical law. Sometimes it reveals deeper forms of order. Quantum information science treats superposition and entanglement as practical resources rather than only as strange philosophical curiosities. This change in attitude is important. Instead of asking only what these features mean, researchers now ask how they can be used. In that way, interpretation gives rise to engineering. Quantum dots are also being developed as spin-photon interfaces, which could help future quantum repeater systems. Such an interface matters because one part of a device may want to store information quietly, while another part may need to send it far away as light. A bridge between those roles is highly valuable. NASA is studying both quantum communication and quantum sensing for future missions. This shows that quantum physics is now part of long-term planning for exploration and space technology, not merely something confined to Earth-based laboratories. The reach of the field is widening gently outward. Quantum states can be pure or mixed. A pure state represents a more complete quantum description, while a mixed state includes uncertainty or unobserved entanglement with outside degrees of freedom. This distinction matters because real experiments often deal with mixtures, where the calm simplicity of an ideal state has already been softened by the surrounding world. Entanglement entropy is one way to measure how strongly a subsystem is tied to the rest of a larger quantum system. It gives a numerical way to express how incomplete a local description can be when the whole carries more structure than the part. This is a quiet but powerful idea because it turns interconnectedness into something that can be studied carefully. Quantum foundations remain lively, partly because the theory is so successful while still leaving room for different ways of understanding what the mathematics means. The equations work with great precision, but the deeper story we tell about them is still open to reflection. This makes quantum physics not only a technical subject, but also an intellectual one. Yet whichever interpretation a person prefers, the experimental predictions of standard quantum mechanics remain the common ground. Nature continues to agree with the formalism. That steady agreement offers a kind of calm center beneath all the conceptual debate. Medical imaging and therapy use technologies deeply shaped by quantum and particle physics research. Techniques for producing beams, detecting radiation, and reading subtle signals were refined through efforts to understand matter at fundamental scales. This is one of the quiet ways basic science returns as care and utility. Quantum sensors are able to measure time, motion, gravity, magnetic fields, and light with sensitivities that often surpass more classical approaches. They do so by using coherence, interference, and quantized responses as strengths. In that sense, they are instruments built around listening to very delicate structure. Space-based quantum sensing is attractive because long free-fall times, different gravitational conditions, and reduced disturbance in some settings can improve sensitivity. Space offers not only distance and view, but also a special environment for measurement. It can become a calm extension of the laboratory. Quantum communication research is also about enabling networked quantum states, not merely about sending ordinary information securely. The goal is deeper than faster messaging. It is to preserve and distribute the character of quantum information itself over meaningful distances. The first quantum revolution gave rise to technologies such as semiconductors and lasers by teaching us how matter behaves. The second focuses more directly on coherence, entanglement, and careful control. This makes the newer era feel quieter and more delicate, because the task is not just to use quantum effects, but to preserve them long enough to guide them. Quantum hardware often improves not only through sharper theory, but through better materials. Cleaner surfaces, fewer defects, and lower loss components can make an enormous difference. In practice, progress often comes from learning how to create a kinder environment for fragile quantum behavior. Many of the most precise tools ever built are precise because they are anchored to repeatable quantum behavior. Their steadiness does not come mainly from size or force, but from fine structure and reliable transitions. There is something restful in that idea, precision born from subtle order. Quantum behavior in large systems is hard to preserve because large systems couple more easily to their surroundings. More parts usually mean more pathways for noise and disturbance. This is why scaling quantum devices is such patient work. The challenge is not only to make them bigger, but to keep them quiet. Some of today's best quantum experiments succeed by creating tiny protected islands of coherence inside much larger ordinary machines. A carefully isolated circuit, trap, or chamber becomes a small place where the quantum state can remain itself a little longer. Much of modern quantum engineering is the art of making these quiet spaces. The ability to cool and trap increasingly exotic systems has become one of the recurring themes of modern quantum physics. Whether the system is an atom, an ion, or something far less familiar, the path to understanding often begins by slowing it, holding it, and giving it a little stillness. One long-term goal of quantum research is to study systems whose complexity grows too quickly for brute force classical calculation. Rather than forcing every answer out by sheer computational effort, physicists are learning to use quantum systems themselves as guides. In that way, nature becomes both the mystery and part of the method for understanding it. And perhaps that is a gentle place to rest tonight. Quantum physics keeps showing that the world is richer, quieter, and more finely connected than it first appears, from the smallest transitions in atoms to the largest instruments built to listen for faint signals. Beneath all the mathematics and machinery, there remains a simple, peaceful truth that careful attention reveals hidden order almost everywhere.